So now we need that integral. Yes?
Why do you have a dx attached to the sum? Is it because you're interchanging them?
I was interchanging but forgot to write the integral that I interchanged. There's the integral that I interchanged. Thank you. I have a certain blackboard behind this, so I missed some of this stuff. Yes?
Why is it important to see this, to evaluate f of x cosine m pi x over L dx?
That's going to be our Fourier coefficient.
Okay, sorry.
F of x is still unknown, right? That's part of the problem. That initial condition comes in here. And we want to get this, we've got all these eigensolutions, but we somehow have to get them to match up to the initial condition.
Okay.
Because that's the one piece we haven't solved. We only solved the boundary value problem. So it's rather important. This is going to be part of our Fourier coefficient.
All right.
So now, I think I've got the slides on this, and so I don't put it down. Of course, everybody knows that integral really well, right? What do you think that integral is that I have over there? Just a guess from before, with the sine functions.
L over 2.
Hmm?
L over 2.
L over 2. That's going to give us an L over 2. So if you do the cosines, if m doesn't equal n, it's going to be 0. Okay? So then that's going to get rid of that infinite sum and only leave us with the b sub m. Right? And then we have to figure out what this integral of the cosine squared. Well, the cosine squared is just like the sine squared, gives you that L over 2. All right? And so we'll go ahead and put that in here. So this is going to be equal to L over 2. And so now you can see, and this is the question, why do we have this thing? We're going to have that those Fourier coefficients, b sub m, are going to be 2 over L, the integral from 0 to L, of f of x cosine m pi x over L dx. Now we still, again, this is something we're going to do in the future. We have to show that we get the nice convergence on it. We're not there yet. Okay, so, and again, this is a problem you've already done in calculus. You've done the squared one, you do the half angle stuff and so forth, and take care of it, and you get that L. And of course, the squared is obviously a positive integrand. It has to give us a non-zero value, doesn't it? The other ones, their harmonics match such that the area divides out. And we get 0. And that's the orthogonality. Okay. So there's that. And so then, oops, this was right in here, f of x equaling that. Then you use the orthogonality part, and we do it. Notice a little difference here. 1 over L with the A0, the AMs have a 2 over L. So that's why I like to sort of separate those two cases. They're really a little bit different. So that 0 eigenvalue really is handled a bit differently than the other eigenvalues. Okay? So, there we go. So forth, orthogonality, okay. And going to this particular solution here, so there's the solution, we can see as t goes to infinity, look at this, as long as n is not 0, n is greater than 0, this is a positive coefficient here. We have exponential decay, right? So this part all goes to 0 for large time, so A0 becomes the solution for the steady state situation. And it's what we said in the beginning. The intuition told us that A0 should be the average initial condition temperature. And that was just the Fourier coefficient with that 0th eigenvalue. I'm hoping I'm showing is that a lot of your intuition should work on this. But now, here's the significant difference on this is Dirichlet sine functions. What was the equilibrium for the Dirichlet conditions?
The linear?
But it's a homogeneous differential equation, homogeneous boundary conditions. You're right, it's linear if you have different values. But if you have homogeneous ones,
Constant.
what's the equilibrium? I put 0 on each end, hold the temperature at 0 at each end.
Mm-hmm.
What's the temperature gonna be through that whole bar? Zero. If I hold it at 0, eventually everything has to be 0, right? That's what we, you stick something into the freezer and it eventually goes down to the temperature of the freezer. You have some pretty melty ice cream, right? You don't have ice cream that has sine functions in there. Okay? You do to start with. All right? Does this make sense? So your intuition should have, but the difference again, once I put the insulated boundary conditions, we go to the cosine series. Okay. We're going to do heat conduction in a ring. Okay. There we have a nice ring. Now the thing about a ring is, it's circular. And so we somehow want to get this back to like our bar, and so the best way to think about it is taking that bar and connecting it together. And just like problem number 4, what is the natural condition here at L and minus L?
Temperature and flux are the same.
Temperature and flux are going to be the same. All right? So on this particular one, now we see what are our boundary conditions. We're going to see that our boundary conditions are going to be that U at L for all time t is the same as U at minus L for all time t, right? And the partial of U with respect to x at L is going to be equal to the partial of U with respect to x at minus L. So now we're going to have those boundary conditions. And notice, if I were to just put a minus here and set that would be equal to 0, that's a homogeneous boundary condition. Minus equals 0. These are U appearing in a linear fashion, right? And so we've got linear homogeneous boundary conditions. Okay. So otherwise this looks, so all we're doing is we're taking this rod, we've done the one-dimensional one, and we're now bending it around, and instead of going from 0 to L, we'll say from minus L to L, connect those two up, and we've got ourselves a nice ring.
Okay, sorry, one question. So, was your point about the homogeneous, that in this instance, regardless of what they're both actually equal to, so it could be like 0, 3, 4, 5, that just means homogeneous?
It's going to be homogeneous because when I subtract, it's 0. This minus this is equal to 0. This minus this is equal to 0. Right? And as you're pointing out, if this temperature is 5 and this temperature is 5, you subtract it out, you're still 5. Okay. So there's our particular heat conduction ring. Yeah.
Is defining it as L and minus L like convenient for the math? Like, Is that just kind of weird?
You have to make a break somewhere.
Okay, yeah.
Have you done complex variables yet?
No.
No. You always have to worry about where you make a cut. It's more complex than complex variables. And so you have to worry about it. But it is an arbitrary position, and tradition says to just set it opposite of the zero on this.
Okay.
Those conditions look very similar to like an even function. But it's the same for the
Oh, yeah.
0th and the first derivative. Like they're both even. In quotes, I mean.
Well, this one's gonna have solutions which are off. So your intuition isn't quite right. This one, so what we've generated so far was the Dirichlet gave rise to the sine series. The Neumann conditions gave rise to the cosine series. This is gonna give us the full Fourier series, which has both sines and cosines. Because if we have a function which is neither even nor odd, we better be able to add odd functions and even functions together, shouldn't we? To be able to match any arbitrary f of x throughout this, it's gonna have to match it up. Okay, so I'm not gonna write all this down because it's pretty repetitious as to what we've done before. Heat equation hasn't changed, separation of variables hasn't changed. Okay. So, what's gonna happen with that? Well, the time varying one, no change on that. Once again, we certainly hope that lambda is greater than or equal to 0. Now, this is an insulated ring, so any heat that's in there should stay in there because of that circular nature of it. So we do expect that there is going to be an eigenfunction at lambda equals 0, don't we? Our intuition tells us we should get some average temperature around that ring from the starting conditions. You start with some arbitrary starting condition, it's going to all average out, and we're going to get a 0, which tells us we should have an eigenvalue lambda equals 0 coming in there. And let me just use the slides for this. So here is our Stern-Liouville problem. Phi double prime plus lambda phi equals 0, lambda minus phi of minus L equals phi of L, and phi prime of minus L is equal to phi prime of L. Okay? Again, that's the matching temperatures at L and minus L, and matching fluxes at minus L and L. Okay? Lambda equals 0. Right? We put lambda equals 0, again, we get the linear function by just integrating twice. Now, just again, to make it into the homogeneous thing, just subtract this, so we're going to have the phi of minus L minus phi of L. Well, that's going to be equal to minus C2L, right? Because we do that, putting the L in there, the C1s cancel out, and so you're going to get minus C2L, so necessarily C2 equals 0. And that's no surprise, we should not have that linear term in there. What about when you do the derivative? Well, you do the derivative on that, we get, the derivative is going to be, it's the C2, 0. When you take the derivative, the C2 is already zeroed out, you get the C1 is equal to 0, so we just get 0, automatic from that. So, you get no information from that, so we can see that C1 is once again arbitrary, C1 being arbitrary, the constant, that says that for lambda 0 equaling 0 being an eigenvalue, you get eigenfunction 1. Just like we did with the cosine. So periodic is giving us that. Any questions on that part? No surprise. Okay. If we put cautious and cinches in there, I'm not gonna go through the details on this. Oops. Let's get Peter here. Then you take care of it, you use the evenness and oddnesses of the caution cinch functions, and then being odd function, you get the C2 equals 0, being an even function, you get the C1 equals 0, and so based on that, we get the trivial solution only if we try to choose the alpha equals less than 0. Not that exciting, but you should, on things like take-home exams and exams, you should show these cases when asked. Sometimes I'll say, okay, you can just cite this case. Once again, with the alpha squared greater than 0, we're going to get our friends cosine and sine in there. Okay, put the cosine and sine function in there. Put in the minus. Put the let's see what I do. What I put here. First boundary condition. So we have the putting in minus L equaling this. Notice from this particular one, cosine being an even function, this cancels this, right? And so we just get 2C2 sine alpha L equals 0, right? And now, what does that tell us? What tells us about the alpha? Well, once again, we want the non-trivial solution. So we want C2 non-zero. So we get eigenvalues n pi over L. Same thing again. What happens if we take the derivative? Well, we take the derivative, this cosine becomes a sine, this sine becomes a cosine, same ones over here. Now what happens is that the C1, we're going to get a 2C1 sine alpha L equaling 0. And so now we'll get the C1 being an eigenvalue. All right, so C1 being non-zero when, once again, alpha n is the n pi over L. Now putting these two things together, look, C1 can be arbitrary, and it goes with the cosine of n pi x over L. And the C2 can be arbitrary, and that goes with the sine. And so what we get now is, once again, so the eigenvalues, or the lambda n's, or the alpha n squared, the n squared pi squared over L squared. The eigenfunctions now are the linear combination an cosine n pi x over L, and we've got to use a different constant of bn sine n pi x over L. But now we get both sine and cosine, not just one of them. So these periodic boundary conditions give us both sines and cosines. And these will lead to what's called the full Fourier series. Looking at those particular ones, so then we can do our product solutions. Product solution, well, just get the A0 for the one. Product solution is going to be this exponential with the decay rate. Notice they're the same eigenvalues with the same decay rates. But then you're going to get the cosine and the sine. And so then what we want to do is we want to do the sum of all those possible ones at 0 to equal our f of x around the entire array from minus. And the orthogonality is going to be what now? We're going to integrate from what to what? Minus L to L of our functions, instead of going from 0 to L. Yes.
And we're not doing this in polar because it's not the whole region, it's just the rod, right?
We'll get to that yet.
Okay.
And that creates a whole different boundary conditions too. But no, this is just a thin ring going around insulated sides And so that's all it is. Okay? Now, superposition principle. Once again, I always like to put the A0 out separate because it really is kind of different. What about that A0? Well, it's quite clearly orthogonal to the cosines. We already showed that. Well, we actually have, because we have not done from minus over. We've only gone from 0. So I better hold back on that. But the superposition principle, we'd like to add infinitely many of them. We add the A0 up front, and then the infinite sum from 1 to infinity, the exponential an cosine and bn sine. And the initial condition, put the 0 in there. The f of x better be this A0, then the sum, notice when you put the 0 in, the exponential goes out, and then we're going to have the an cosine n pi x over L plus the bn sine n pi x over L. And once again, since our domain is from minus L to L, we want to integrate from minus L to L. So, if you integrate from minus L to L of the cosine functions, what they do is for n not equal to m, then you get 0, orthogonality of those. For n equal to m, you get L, and when n equals m equals 0, you get 2L. For the sine, well, the sine, we don't worry about the, so notice when n equals m, we're saying 1 and 1. That's what we're really doing, the first line. Sine does not have the n equals m equals 0. It only gets the 0 and L. Okay? And when you look at sine and cosine, those particular ones, they have orthogonality between each other, so that we don't get a mixing. We don't have a problem with the sines and cosines mixing. They themselves are orthogonal with each other. So we really do have this independent set of all these different eigenfunctions. Okay. And the coefficients, well, based on this, we're going to get 1 over 2L. Isn't that the average of the f of x from minus L to L? Because that's linked to L. So that's the average temperature of the initial condition. Then we get the 1 over L. Remember, it was 1 over L, the integral, when we went from 0 to L, and we got 2 over L. Now we're getting 1 over L from minus L to L, f of x goes to L. Okay? And see, if the f of x was an odd function, what would be true about this integral? If f of x was an odd function, what's true about this integral right here? It would be 0, right? And if f of x is an even function, this one's 0, okay? So taking advantage of symmetry properties can help you on some of your problems in zeroing out for some of your Fourier coefficients. All right. Any questions on that? You can see these problems get kind of a little fast. But I want you to be thinking of, I hope you realize, well, I mean, you're already realizing some of these integrals are not exactly pretty to work out by hand. You may want to take advantage of things like maple. In your homeworks and stuff like that, you should just go ahead and put a little arrow and say maple equals this. Or Wolfram alpha equals this. Wolfram alpha has but, or you could also say that you already know, hey, f of x was an odd function, that's 0. But do tell me that you knew that it was an odd function. That's 0. So remember some of those things that you learned back in calculus, well, you probably forgot from it, but There were reasons you did those problems about things being even and odd and stuff, to simplify your integrations. So we want to simplify whenever we can do that. All right, so the next thing we're going to do is Laplace's equation. We're going to move to a whole different partial differential equation. And then we'll get to our nice circular disc.